equation to have a constant error variance instead of the sigma square instead of sigma square xi. So it is important to note that to estimate the transform regression model, we must use the regression through the origin estimating procedure. So now, after we divide, it's just like we have two regressors. Just like we have two regressors, this is our new dependent variable. This one, the first regressor, second regressor. So now the originally intercept now becomes just like new. In the transfer equation, just a new regressor, 1 over square root of xi. So we must use the regression through the origin. So meaning that without intercept, this one without intercept. So because intercept, the origin intercept now becomes a new regressor. So this model, equation 1. This is equation 1, the origin 1. And then, but this model has the problem characteristic based on the first two tests, Bertrand Habe, Bertrand laser. Habe, I remember. I think Habe also has problem. Habe there's no. For the others, there's only the first two. The first two suggest there is a problem for heteroscedasticity. So how to remedy the problem? So if let's say if we believe that the error variance of this proportional to the value of x, proportional to the value of sales, then we can use this approach. So we divide the equation by the square root of the sales. Okay. So this one, maybe we estimate here. So we estimate here. Or maybe you can re-estimate. You can. I mean, this one also. You go to quick estimate equation. So you estimate the transform equation, that is the R&D expenditure, divide by square root of the sales. Square root just SQR. And then the original C, now it becomes 1 over square root of sales. SQR. And then we have, you refer to this one, and then this one, square root of sales, space SQR. Okay, it's okay. So we name as I mean, we can delete as one. Never mind. We can name as question 2. So I want to have question 1 and the question and the latest one. This one. Okay. So previously, when we performed the original equation, it fails the Bertrand test. This one, it failed the test. Just record that previously when we performed the test, Bertrand test, it failed because p value is 0.04. But now after we transform, by assuming that the error variance proportional to the value of sales, we try this approach. We divide by the square root of sales, and then if you perform the test again, you redo the test now. Bertrand and this now p value now larger than 0.5. So we managed to lessen problem. So in terms of estimate, remember, estimate is fine. The estimate of the parameters is okay. But the problem is when there is the problem of heteroscedasticity, then we do have unreliable standard error, t-state, and p-value. So the reason why we transform the equation in order to help us to get more reliable estimate of standard error, t-state, and p-value, so that we are more confident to make conclusion whether the sales have significant influence or not on the dependent variable, the ID explanation. Okay, so basically we remedy the problem in order to get reliable result or conclusion of the hypothesis testing lah. Yeah. But in terms of estimates, okay, estimate you can use. You can use this one because it is still unbiased estimator. Okay, we can use this estimate, the estimate of the 0.03, the estimate of the slope coefficient, so that you can say that when sales increase 1 unit, $1 for example, R&D and the expenditure on R&D increased by 3 cents, 0.03 to 3 cents. So you can use this result of estimation to make interpretation, but we are not able to rely on this because it makes the estimate of standard error to be incorrect. Okay, so we have to remedy and then make conclusion based on this one. Okay, so if for the test it says that you manage to remedy the problem, then you can form hypothesis testing based on this. So this one is still the same conclusions. We can conclude that it is significant. Okay, now if let's say the error variance is proportional to the square of x squared, not x but x squared. If the estimated residuals show a pattern, you check the graph of residual, it shows that you can see more clearly when you produce plot between the square of residual against the x squared, the square of x. So proportional to x squared, which suggests that the error variance is not linearly related to x but increases proportional to the square of x. Symbolically, the error variance of u, the variance of the u or the error variance equal to sigma square xi square, not x but xi square or the square of x. So in this case, the appropriate transformation is to divide both sides of the model by xi rather than the square root of x. So divide by x, not square root of x. So each of the equation. So originally we have dependent variable y divided by x, and then the original intercept now become 1 divided by xi, and then this one is x over x, so it become 1. X over x just 1. So it's just like we have a new constant here. So it's just like we transform this to be a new intercept. Okay, and then this one is our new the transform error term. Okay, the transform error term vi equal to ui over xi. Similarly, we can verify easily that the error term vi is homoscedastic. You refer to the this one for a second case. If let's say error variance proportional to xi, which is given by this, the variance of ui equal to the variance of ui equal to sigma square xi square. So the transform error term in the transform equation given by this. So if we take square of this, you get this. So the variance of the vi, the variance of the new error term vi is given by this. So this one you can take out. So 1 over x squared. So we have this, and we know that the variance of u is given by this. So you can replace it here. So this xi can cancel out, xi square, xi cancel out. So we have sigma square just like before. Okay, so it means that if we believe that it's proportional to the square of x, then we divide by the value of x, not the square of x, but the value of x. So that the new transform error term now has error variance equal to sigma square. It does not depend on x anymore, but it's just a constant value. So for a given example, let's say now we believe that, or we are based on the graph, we believe that or maybe after you perform the test, if it still fail the test, you perform the push plug and land test, it still fail the test, and then you can try this one out. Maybe it is proportional, but remember that the approach that we are going to consider, not all able to solve the problem, and sometimes the use of certain approach unable to remedy the problem. Okay, so this is just a number of available or possible approach that we can use in order to remedy the problems of heteroscedasticity, but not necessarily that the approach, each of this approach able to lessen or to overcome or to remedy the problem. So let's say it is a proportional to n square, so we need to divide, so we re-estimate divide by sales instead of square root of sales. And 1 over sales, the originally it is intercept, but now 1 over sales, and then this one sales divided by sales, it is 1, so it just equivalent to have a constant, we put C. So we get this. So the question now, basically this is represent the estimate for the slope for sales original equation. So our C here is the estimate of the slope parameter for the sales in the original equation. But what we want to do now, we want to have reliable estimate of standard error. So reliable or not, so you have to test. So in this case, so if you perform the test again, heteroscedasticity test, Pragan complete test, it's a p-value even better than previous one, I think. So this one 0.22 greater than 0.05. So meaning that we can rely on this to perform hypothesis testing. So we say that we reject the analysis, we conclude that sales have significant influence on the R&D expenditure. Okay. In terms of estimate, you can just use this one. Okay, the slope, the original estimate, it is fine. You can use it because it is still unbiased. It is unbiased. The problem is here. The problem is on the standard error. Okay, but this one also quite similar. So notice that an interesting feature is that what was originally the slope coefficient now becomes the intercept. Okay, this one. What the originally the slope coefficient for the sales vector 1 now become an intercept. And that what was originally the intercept now become the slope coefficient. Original intercept now become the slope. This change, however, is only for estimation in order to provide us the reliable estimate of the standard error. Multiplying by the xi on both sides, we get back the original. So this one is the one that process now. So there are two possible ways of to elevate the problem. So this the next possible approach that to re-specify the model. So re-specification of the model. Instead of speculating about the value of the sigma I square and the error variance, sometimes a re-specification choosing a different function form can reduce heteroscedasticity. For example, instead of running the linear invariable regression, if we estimate the model in log form, it often reduces the heteroscedasticity problem. That is, if we estimate log of dependent variable against log of the independent variables, the heteroscedasticity problem may be less serious, or maybe we are able to overcome the problem, totally overcome the problem. So the log transformation compress the scales in which the variables are measured, thereby reducing a tenfold difference between two values to twofold difference. As an example, let's say in the original values of y or x, the value is 90, which is 10 times of 9. So after we use log transformation, we compress the value. So log of 90 now is equal to 4.49, which is only twice as large as the log of 9, which is equal to 2.1. So we compress the value to make smaller. So by doing so, it can help to reduce to have the model to reduce to have what we call that the different value of the error term, the different value of the error variance. Okay, so it helps to make the error variance to be not that much different. Okay, based on across different value of x. So for this given example, another possible solution is by using different functional form instead of using original R&D and sales variable. We use log, double log model for example. So log of sales, log of R&D expenditure, and then log of sales. So you have okay. So you have more than one x. You can apply log transformation on all x. No? So let's say you have another x, so we can log of x as well. Okay, so we get this one. So now the question is this one reliable or not for us to conclude whether the log of sales significance typically influence the log of the, or you can interpret as before. I mean, because the log model you can interpret as elasticity %. Okay, I mean interpretation okay, you can interpret as this one. It's okay. The estimate is still unbiased, but this one whether the half system it is reliable or not. So you perform a test as before. Let's say you just perform a test using the one of the test, one pattern of rate. It is now it passed the test 0.1. If you perform test at 5 something level, now it is p-value greater than 0.05. So we will reject. Conclude that there is no heteroscedasticity. I mean the variance are not, the error variance are not different. It's just the same, constant. Based on the tested what we call that the test that we use much program covering the tested pattern of the error, heteroscedastic error. Okay, but you can also perform the other test as well. So this one let's say we just perform a test using the program test. Now it improves using the use of a different functional form allows us to improve to make the model now pass the program covering. Other possible solution, redefine the variables, regress per capita dependent variable against per capita independent variables. For example, in study of expenditure on travel and the corresponding income for 51 cities or countries, we might expect that the error variance are heteroscedastic and increase with population size. Cities, countries with large population are likely to have greater variation in the expenditure on travel than small. So let's say you collect data. Let's say you have two variables. You want to explain the travel expenditure. Your Y is travel expenditure, so your dependent variable is one, expenditure on travel. Okay, and then you collect data total amount of expenditure from different cities. Okay, for example, you collect data the total amount of expenditure travel on that travel for Kuala Lumpur, for example, and then you also has the total amount of expenditure for other smaller cities. Then you have the problem like before. So for example, this one, whenever you have this one, so for example, let's say you have the travel expenditure, and then you have total income. Okay, total income for everyone. I mean for the whole population. So let's say for KL, for Lumpur, you have this one. Then this one for smaller cities, Ipoh for example, or other Alustar. So because of that, you will have the problem because you have some of the observation has small value of Y and X, and then other value of X, Y and X has large value of Y and X, and then you can produce the different value of error term. So this one has smaller error, this one has large value of error, and then you make your error variance to be different. So in order to overcome the problem, one possible way is to calculate or to use the per capita variable. So meaning that you divide by number of people. So let's say income total expenditure in KL, Kuala Lumpur, you divide by number of population, how many people in Kuala Lumpur, so that you get average of expenditure per person. Okay, and you do the same for other cities as well. For Ipoh, in Ipoh you divide, you calculate the average expenditure and average income for each people in Ipoh, for example. So you by doing so, you are able to lessen the problems of heteroscedasticity, or even to avoid the problem. Okay, use the per capita variable. So for the example that we had before, it's also possible if you are able to get, for example, this one you have the problem. This one we have R&D expenditure and sales. So if there is any way for you to recalculate, so you get average instead of the total sales, total R&D expenditures, you are able to recalculate and use the average value, and then you may be able to remedy the problem. I mean, to avoid the problem of heteroscedasticity as well for this data. Okay, if you are able to do so, you can do that. You can consider to do it. Use the per capita or the average, for example. Okay, instead of the total amount, because different size of companies here has different values of sales, larger value of sales. Larger company has larger sales and R&D expenditures compared to smaller companies. So this one, you have this kind of data, so calculate, use regress per capita against the per capita for the other independent variable. The last possible way is using the robust standard error. So this one, because of white heteroscedasticity corrected standard errors, as we have noted in the present of heteroscedasticity, the ordinary least square estimator, although unbiased, are inefficient, although the average of all possible estimates are equal to the true value, but it is no longer efficient. So meaning that it affects the variance of the estimator. So as the result, the conventionally computed standard errors and the t-sensitivity of the estimator are suspect. White has developed an estimating procedure that produces an area of estimated regression coefficient that takes into account heteroscedasticity. As a result, we can continue to use the T and F test for hypothesis testing, except that they are now valid asymptotically, that is in last sample. It is advisable to present the usual standard errors as well as the white heteroscedasticity corrected standard error for comparative purpose, but keep in mind that white methodology is strictly speaking applicable in last sample. So if you want to use this approach as a remedial measures, you have to make sure you have enough data set, large sample size. Okay. So when we talk about large sample size, normally large sample size refers to the observation greater than 30, but this one you should aim to have larger. Now you want to use this one, try to have larger sample size. That's why last week I mentioned to you, try for your group assignment, try to have at least 50 observation. Okay. If you refer to one of the reference book, textbook reference book, it has one example of the solution for heteroscedasticity using this one, robust standard error, and for that example, it has about 45 observation. So I mean, 45 still okay lah, but try to have. I encourage you to have at least 50, not 50. Even larger is better. Okay, larger is better to produce more reliable estimate. So how to use this approach? When you estimate the model, for example, this one we estimate the model. The original model RD, C, sales. You go to option. You select, instead of ordinary, you select I think this one Hugo White. It will produce an estimate. It produces an estimate of standard error that is less or unaffected by the presence of heteroscedasticity problem. Okay, like this, then okay. But this one we have to trust lah, meaning that's why I mentioned earlier. You need to make sure you have large enough sample size, because we are unable to check whether the use of this approach managed to lessen the problem or avoid the problem. Because if you perform the test again, you produce the same test, the same result of test. For example, if you perform a test, heteroscedasticity, basically it produces the same test like the original model. So basically this one you have to trust. You use the approach, you have to make sure you have sufficient data, and then we just trust that now the estimate of the error is reliable for us to make hypothesis testing. But this one, for this example, it's not. You should not trust because it is. We have small sample size, 18 only. Okay, so 18. We should not perform. You should not use the approach for this example because we have small sample size. I just want to show you how. So if you want to use this approach, robust standard error, then you have to make sure you have large enough sample size. Okay, try to have 50 or around 50 or above. But there is an example given one of the books. It used 45 observation for this approach. So 45 is still acceptable. So you notice that this is the original estimate. The estimate exactly the same after you use the robust standard error. The estimate exactly the same. So I mentioned before that the estimate, the original model is okay. It does not. I mean, even though it may not close to the true value, but it is still unbiased. But the problem when we have a heteroscedasticity problem here, we have the problem with standard error. So by using robust standard error, it helps us to provide more reliable. But this one we cannot use actually in the real practice. You should not use for small sample. So we only have 18 observation. Okay. So we still have about 20 minutes. Maybe we can do the first question for the lab session 6. Okay, the mention about Robertson error given here. You open this. Basically, we have different types of Roberts standard error, estimated Robertson error. The one that we used just now, that you go right. When you read here, basically we have this one. For the case of heteroclasticity, we can use this one, the AC. But later next week we discuss about autocorrelation, and we can use this one. Heteroclasticity and autocorrelation process for activities. Do the first question. You do the first question. So we have almost, okay, so question number 1, what is meant by heteroclasticity? That as what we discussed earlier, so I explained to you that it represents the problem when we have we have a different what we call the error variance, non-constant error variance. Heteroclasticity means that the variance of the error term in a regression model does not remain constant between different observations. The radius square estimated are still unbiased, but they are no longer efficient. So estimate we can use, but in terms of how testing, then we have problem now. Testing. Since the estimated standard error of the radius square estimated may be biased, the resulting t ratios are likely to be biased too. As a result, usual combined interval, testing procedure, etc. are likely to be of questionable value. So question number 2, we have almost the same data, but now we have different dependent variable. Probably try to redo it, but try to just use use now. Later at home you can do the manual one, the manual approach. So this one, question number 2, this one. Estimate the regression by regressing the RND expenditure against profit. So you can estimate as usual. RD, EXP, C space, C and profit. Obtain residual and plot against the exposure variable without any evidence of heteroclasticity. So you can produce plot. So this one okay. So you go to view actual fitted residual table. So you have this actual fitted y hat residual. You can see residual for different value of x. Now you have larger spread of residual, value of residual. The size of residual getting bigger. Okay. So now if you want, the question asks you to plot the residual against the value of x, the profit. So residual against profit, you can just let's say now we want to produce plot, scatter plot, profit as your x axis, residual as y axis. So you have to click profit first, and then click the receipt. The price control, click receipt. You can right click, open as group. You go to view, graph, scatter plot. So based on the graph, we can see now. So as the value of profit increase, the size of the error, estimate of error receivable, the value, the spread getting larger, the spread. So there seems to be some evidence of heteroscedasticity in the data in the model. C. Verify your qualitative conclusion by conducting the branch bug offering, that's the Harvey and Arch test. So the estimated model is now, you can perform the test. So this one again, I will not show the manual one, you can do the manual one again at home. So we just use e-views. So again, I mentioned for your midterm test, just use the just use e-views to produce the result, no need to do manual approach. So you estimate the model, for example, this one, you estimate, you get the result, and then to perform the test, just go to view, residual diagnostic, heteroscedasticity test, perform the test using the 3 tests. Perception of 4 tests. Perception, laser, Harvey, Arch. So for the perception, the result suggests there is heteroscedasticity problem. How about laser? Okay, laser, this one. Also the same. Okay, and Harvey Arch. Harvey also failed. How about Arch? Arch also failed. So you failed all 4. So after you remedy, basically the good idea is that you test for all. I mean, previous example, we remedy the problem and we just perform the test using perception. But it's good that you perform using all the tests. Although it's not compulsory, as mentioned before, you refer to the article. This article, for example, some of them just use white test. But again, you refer to the example given in lecture. The white test fails to detect a problem. It says there is no problem, but the perception says there is a problem. And similar with the laser test as well. Okay, so so you have to decide whether you are willing to take that risk, meaning that white test has a less chance of capturing the problem, but it is acceptable to use it. So this one, the next question: if there is evidence of heteroscedasticity, how do you transform the data? So in terms of transform, we have a weighted square. So we have 2, whether we assume it is the error bar proportional to x or proportional to x squared. So we can try the first assumption. So let's say the first assumption that it is proportional to x, then we divide by square root of profit. Okay, this one. So you estimate. Maybe we re-estimate another one. So we estimate the transform equation. So we have RDEXP space divided by square root of SQR of profit. And then the original intercept now become 1 over square root profit. And then we have profit divided by square root profit, we have square root profit. So okay, so name as equation 2 or equation 1. So this is the transform. So now the question is, the original one is 1, the original is the original. So estimate 0.36. This is the transform equation 0.37. So slightly different. Now the question is whether this is reliable or not. The original one not reliable, this is not reliable because we have a problem. So this one reliable or not, so you perform the test now. For example, you perform the test, first pattern test. So it still failed, 0.03 less than 0.05. So the use of the first assumption, proportional to x, is unable to remedy the problem, still failed the test. So now consider another assumption. If let's say we assume that the error bar proportional to x squared. So if proportional to x squared, what you need to do? You divide by profit, not square of profit. So divide by RAD exponential, divide by profit itself. And then our original intercept now become 1 over profit. Profit divided by profit equal to 1. It becomes a new constant. Okay. So now this is reliable now. To perform the test again now. You perform the test. You see heteroscedasticity berbagai. Now it is created that. So meaning that the error variance for this is proportional to x squared. Then not instead of x is proportional to x squared. So you use this one the result of this. The alternative approach is by using different re-specified model or using different functional form. Question number 3, yeah. Question number 3, use different functional form using log. So instead of using original values, we try to use log. So we re-estimate using log. So log of RD expenditure, RDEXP, spacey log profit. But in terms of interpretation, you have to be careful. So you have to interpret at percent this one, because using double log model, interpret at percent elasticity. You cannot interpret as usual. You have to interpret as elasticity. So when profit increase 1%, the R&D expenditure increase how many percent? By 99%. No, 0.99%, not 99%. 0.99%. Okay. So this one reliable now. Can we make hypothesis testing based on this? Can we set the result of hypothesis testing based on this? So you test now. For the test, let's say just partial profit. Now it is okay lah. So we can use. Yeah. For 3B, apply code effect fund. That one I leave it to you to do at home. You need to sort. If you're using the sorted data, so we have using the sorted. So meaning after sort from smaller to highest, and then you remove the middle one. Just like what we did earlier, and then estimate the first part, second part, the first subsample, second subsample, and then you calculate. Question number 4. P48 next week lah. So question number 4, will you discuss this period? Can? Or you want to discuss now? Yes, will. So I just afraid that some of you want